To calculate the number of modes we would expect to see in a vibrational spectrum, we can use symmetry. And the way we're going to do that is to develop a reducible representation for all the degrees of freedom, and then figure out how to reduce that representation to calculate the number of IR and Raman active modes. So our question for ourselves, or our task, I guess, is to predict the number of signals in the IR and Raman spectrum of, in this example, sulfur trioxide. So here's our steps for being able to do that. Determine the point group, determine the number of vibrational degrees of freedom, develop a reducible representation, reduce that representation to the sum of irreducible representations, and then determine the number of vibrational modes and assign them to IR and Raman active. This is going to take a little while, so feel free to pause and come back to this as we go along. So the first step is determine the point group of sulfur trioxide. The point group of sulfur trioxide is D3H, and we're going to need that going forward. The other thing we need to do is determine the number of vibrational degrees of freedom. The number of vibrational degrees of freedom is equal to 3n minus 6, where n is the total number of atoms. In the case of a linear molecule, that would be 3n minus 5, because that infinite rotation axis sort of takes away one of the degrees of freedom. So here, the n would be 4, so 3n minus 6 equals 6 vibrational modes. So total degrees of freedom would be 3n, 12 modes, but only 6 of them are vibrational modes. Okay, so we'll keep that in mind as we go forward, and we'll see how we'll be able to use that to check ourselves at the end. Okay, so this part is probably new for you. Our goal is to develop a reducible representation for molecular motion. The way we do that is to think about each of the symmetry operations in the D3H point group. That's why we needed to determine the point group. And decide how many of the atoms are unmoved, unchanged, when each of those operations is performed. Okay, so let's start with the E operation. So if we pick the molecule up and set it back down, all 4 of the atoms remain unchanged. So we'll put a 4 in that box. If we do a C3, so the C3 is coming in and out of the screen through the sulfur atom. And if we do a C3 operation, we'll see that only the sulfur atom remains unchanged. The other atoms move. If we do the C2 operation, so that's in the plane of the screen, going through one of the sulfur-oxygen bonds, then we see that 2 of those atoms remain unchanged. The sigma H is the plane of the screen, and if we sort of cut through all of those atoms, we see that all 4 remain unshifted. And finally, if we do an S3, so we rotate by 120 degrees, and then reflect, we see that the sulfur atom remains in the same place, but each of the oxygen atoms is shifted. Finally, the sigma V's, which go through each of the sulfur-oxygen bonds, we see that the sulfur and the oxygen remain in the same place, but 2 of the oxygens move, so 2 stay the same. Okay, so now we need to figure out how each of those unchanged atoms contribute to the total degrees of freedom. And so we have a row here for something called contributions per atom. Now you can see there's a little chart on the right that gives us the contributions per atom for each of the symmetry operations. So in the case of the identity operation, we see that E gives us 3 contributions per atom, so we'll put a 3 in that box. C3 gives us 0. C2 gives us a -1. Sigma H gives us 1. Any sigma, they're all the same, give us 1. And S3 is -2. And a sigma V, that's also going to give us 1 because it's another sigma. So where do those numbers come from? They come from the transformation matrices that are used to develop the character table. So we'll talk more about that in a second. Now, we can put these together by multiplying down each column to get gamma total, which is the total reducible representation for all of the degrees of freedom. So 4 times 3 is 12. 1 times 0 is 0. 2 times negative 1 is negative 2. 4 times 1 is 4. 1 times negative 2 is negative 2. And 2 times 1 is 2. So this vector, this one-dimensional array here, 12, 0, negative 2, 4, negative 2, 2, that is the reducible representation that represents the symmetries of all of the motions, translation, rotation, and vibration that sulfur trioxide can have. So again, we wondered, like, where does this come from? And so these contributions per atom come from the transformation matrices. So if we think about the identity matrix, we remember that the diagonal elements represent the x, the y, and the z direction. So if you pick up and put back down a molecule, the x, y, and z directions all remain unchanged. But if you think about, if you rotate, if you do a C2 around the z-axis, the z-axis still points in the same direction, but think about doing a C2 around 180 degrees around the z-axis. The x and y now point in the opposite direction, so they're given negative ones in that matrix. Now if you add together the diagonal elements, the trace of the matrix, you get negative 1 plus negative 1 plus 1, which is a net of negative 1, so that's where that number comes from. We can do similar operations with each of the transformation matrices and get to the contributions per atom. In your case, contributions per atom is not something you need to memorize. So instead, you can look it up in the table that is located on the back page of your character table booklet. Okay, so now that we have a reducible representation, which I've put here at the bottom again, we need to reduce that representation to the sum of irreducible representations. And so remember, the irreducible representations are the A1 prime, A2 prime designations in our character table. So we use our reduction formula to do that, which is up here at the top. So the number of irreducible representations of a given type, so for example, the number of A1 primes that are represented in the reducible representation is given by 1 over the order, which we can calculate for this point group. And then we have this sum, where for each of the operations, the number of operations in that class, which is given this blue box, it's the coefficient in front of each of the operations. Next is the character of the reducible representation. So, for example, for the E, the character of that reducible representation is 12, the first column, times the character of that irreducible representation. So in the case of the A1 prime is 1. And then we work through. We go to the C3, where we see that the number of operations in the class is 2, the character of the reducible representation is 0, and the character of the irreducible representation is again 1. Okay, so let's see how that works. So in the case of the A1 prime, we're going to start, so how many A1 primes do we need in our reducible representation? We need the order, which here is 12. And then we're going to work through the sum of each of the elements, each of the operations in this class. Okay, so once again, we said the number of operations in the class, that's 1 in the case of E. We said that there's 12 in the reducible representation, and that the character of the irreducible representation is 1. Now we're going to go to, so that was for E. And so next we're going to do for C3. And so we see that we've got 2 times 0 times 1. And we're going to do the same thing for the C2, where we've got 3 times -2 from the irreducible representation times 1. And then we're going to go to the sigma h. And we've got 1 times 4 times 1. And we're going to keep doing that. So for sigma h, next we're going to go to S3. And we've got 2 times -2 times 1. And now we've got the last one, the sigma v, and we see we've got 3 times 2 times 1. Okay, so if we add all of that together, we've got 12 plus 0 plus -6 plus 4 plus -4 plus 6. And so if we sort of add all of those together, we get 12. And then if we divide by the order, we get 12 over 12 equals 1. So that means that there is one A1 prime that needs to be part of our reducible representation. So one of the irreducible representations is A1 prime. Now, we're going to work through each of those symmetry, each of the irreducible representations. So go through each row and do the same analysis. So pause here and see if you can work through the same thing. Okay, once you've done that, you'll work out that the reducible representation, gamma total, the 12, 0, -2, 4, -2, 2, can be represented by adding together one A1 prime, one A2 prime, 3 E primes, 2 A2 double primes, and an E double prime. So if you took those rows in the character table and you added together the characters, the numbers in each of those columns, you could get our reducible representation. This is a unique solution. There is no other way to come up with that combination, with the combination 12, 0, -2, 4, -2, 2. So these irreducible representations, this sum, these represent the 12 degrees of freedom, the symmetries of the molecular motions of translation, vibration, and rotation. So the total degrees of freedom were 12, which was 3 times 4 the number of atoms. And so here we see that we also have 12 degrees of freedom because we have 1 A1, 1 A2 prime, that's 2, 3 E prime. So E's count as 2 degrees of freedom that are equal in energy. We'll talk more about that. So that's 6 for a total of 8. 2 A primes, that's 10, plus an E double prime, which once again is 2 for the price of 1. So that's a total of 12. So we have 12 total degrees of freedom, and look here, we have 12 irreducible representations representing those modes. But now we're really interested in the vibrational modes. So how do we figure out which of these symmetry labels, these irreducible representations, represent vibrational modes? So we can figure out the vibrational modes by subtracting the translational and rotational modes. It's easy for us to find the symmetries of the translation and rotational modes using the character table. So translational modes, that's translation is just movement in the X, Y, or Z direction. Those are going to have the same symmetry as the X and Y and Z mathematical operations. So we can find X and Y and Z mathematical operations in the character table. Okay, and so we know that the vibrational modes will be the total minus translation minus rotation. So we can subtract off an E prime mode and an A2 double prime mode. Okay, We can do the same thing for the rotation. The rotational modes have the same symmetry as the R's, the R functions. So RZ and RX and RY. Okay, so we can subtract off an A2 prime mode, that A2 prime mode in our reducible representation is the rotation around the z-axis. And then the E double prime mode was the rotation around x and y. Okay, so if we subtract it down, we see that our vibrational modes are an A1 prime. So the A2 prime basically got subtracted out. We have 2 E primes left because one of them was translation along x and y. And then we've got 1 A2 double prime, and then the E primes go away. Okay, so our vibrational modes, the sum of vibrational modes, is an A1 prime, 2 E prime modes, and an A2 double prime. So remember at the beginning we said that there were 6 vibrational degrees of freedom. And so here we have 1 from A1 prime, 2 times 2 from the E primes. So the E primes represent 2 modes that have the same energy. So there are 2 of them. And then an A2 double prime mode. So there's a total of 6 vibrational modes for this molecule that are represented by these 4 symmetry labels: an A1 prime, 2 E primes, and an A2 double prime. Now, which of these would we expect to be IR or Raman active? We can also figure that out by the character table. So the IR active modes had the same symmetry as the X, the Y, or the Z vectors. And the Raman active modes have the same symmetries as any of these two-dimensional functions. So the x squared plus y squared, the z squared, etc. Okay, so the IR modes have the same symmetry as x, y, and z because the IR selection rule is the change in dipole moment. And so the change in dipole moment has the same symmetry as an x, y, or z vector function. Okay, so we're looking for which modes have x, y, or z symmetry. All right, so if we look at our reducible, our sum of irreducible representations, we see that the E prime modes will be IR active, and the A2 double prime mode will be IR active. And so in the IR spectrum, we would expect to see 3 different signals. One for one of the E primes, another for another E prime, which will be at a different energy, and one for the A2 double prime. For the Raman spectrum, so the Raman modes are going to have the same symmetry as any of the functions in that final rightmost column, the squared functions. And the reason that Raman active modes have those symmetries is that the Raman selection rule is change in polarizability. So imagine sort of stretching the molecule in 2 dimensions. It's going to have the same symmetry as those functions. So if we look at our vibrational modes, we see that A1 prime will be Raman active because it has the same symmetry as x squared plus y squared or z squared. The E prime modes will also be Raman active, so that'll be in both spectra. And but the A2 double prime, it has no function in that rightmost column, so it will not be in the Raman spectrum. Okay, so we're going to expect to see 3 signals in the Raman spectrum, 3 signals in the IR spectrum, and 2 of those signals are going to be at the same energy, representing the E prime modes, and 2 of them are going to be different. So if we were to look at the experimental spectrum, so here we see, if we calculate the vibrational modes, then we get, we can see we get A1 prime, A2, E prime, and E prime, and that these represent stretches and deformations of the molecule. And we can calculate what frequencies we expect to see those. And then, in fact, if you measure the spectrum, you can see that the A1 prime vibrational mode is missing in the infrared spectrum because it's not infrared active. But we get the A2 and the E prime modes. Likewise, the A1 prime is present in the Raman spectrum, but the A2 mode is not present in the Raman spectrum. But then we see the two different E modes at the same energies. So our group theory explanation for what we expect to see in the IR spectrum and the experimental spectrum match. If you want to see what these motions actually are, you can go to this MolCalc site here, and you can actually look at the like little movies of the vibrational modes of sulfur trioxide. So that way you can see that the different modes and see the spectra.